Welcome back to the Additive Snack podcast. I'm your host, Fabian Alefeld, coming to you from freezing cold Austin, Texas today. Today, we're venturing into a very exciting realm of additive manufacturing, some that even consumers can see from time to time, and that is the innovative and intricate world of digital foam, really an evolution of polymer lattice structures. Now, in the past, developing applications for polymer lattice structures, especially for performance applications, has been quite challenging, if we're being honest. You need to consider many different aspects from design all the way into printing and post-processing, not to even forget about materials. And all of these parts and aspects of the value chain also influence each other. And that gets complex real quick. Now, a few key players, the ones that we have in this podcast today, out of the industry came together, and hopefully more will join this initiative, to form the Digital Foam Architects Network. This network intends to increase accessibility, scalability, and really speed of development for especially performance-based data structures. And we've invited some of the brightest minds in that space to today's episode. So joining us today, we have Pierre Gonnetan from Arkema. He's a key account and business development manager. We have Mike Schorr, the general manager at DyeMansion. Nick Florek, the CEO of General Lattice. And we have Dr. Dave Krzeminski, senior consultant at EOS and expert in polymer lattice structures here. So without further delay, welcome you all to Additive Snack.
Thank you very much. Awesome. Thanks for having us.
Thank you. So this is actually the first true panel discussion we've done on Additive Snacks. We're giving this a shot, and I'm really excited for it because I think we're going to have some really interesting conversations. But before we dive into the intricacies of the whole process of developing digital foam applications, I want to ask you a question, Nick, and that is, can you actually take us back a little bit into the history of lattice structures and additive manufacturing, and possibly even explain some of the key terminologies that we'll talk about today to make sure our listeners are familiar with the concept?
Yeah, absolutely. First of all, thanks for having myself and General Lattice on. I think this is a great panel to have, considering we have every aspect of what really makes up digital foam, right? So you have the design component, General Lattice hammers that out, EOS with the hardware, Arkema, the materials, and DyeMansion with the post-processing. I think it's really important to start off by mentioning it takes all of these things to really develop digital materials. Everyone needs to do their own part to really play together and develop successful applications. So thanks for setting this up. But yeah, to talk a little bit about the history of lattice structures, they've really been a fundamental component of 3D printing from the onset. Back to the early days of more simple technology like an FDM printer, you need supports, right? So inherently, lattice structures are acting in the way of supports out of the kind of first early use cases. But when you look at additive in general, there's three main ingredients for success from a design aspect in terms of what works well for production, how do you add value, how do you really enhance the application. And we at General Lattice think of those three ingredients as using additive to do things like part consolidation, using additive for things like mass customization and personalization, and using it for increased design freedom. And so that's really where the lattice structure plays its part. And so these ingredients, I think, are very much meant to be mixed and interchanged, and hopefully the ideal application has a bit of everything. But when you look at lattice structures, there's three main categories that we look at. There's beam-based lattice structures, so you're just beam and nodes that you're connecting in various techniques. There's TPMS-based lattice structures, which stands for triply periodic minimal surface. So these are unique geometries that are periodically repeating, and they bring a lot of really interesting properties along with them. And then there's plate-based lattice structures, which are more just planar plates that are arranged in different orientations, and these can be 3D or more of 2.5D, like a honeycomb sort of structure. Those are the main categories that we really look at. And then the last thing I'll touch on at a high level is the different methodologies for generating lattice structures. You can use traditional boundary representations within a normal CAD platform. You can use mesh-based generation methods, and then a newer form of design, implicit, which can have some tremendous aspects in terms of speed. So you got to always think about data and how complex these lattice structures are and how can we really solve the data challenge from both a design and actually getting the file to the printer perspective. A lot of different things to think about there, but the last thing I'll mention is just some high-level application spaces or benefits of lattice structures. The easiest one that most people probably think of is lightweighting for different strengths to weight optimizations. Energy absorption's another really exciting one, especially in the polymer space. So how can we start to create better performing foams, for instance? And then when you get into metals and more rigid materials, there's really interesting applications within thermal management, RF applications. I think really lattice structures exist everywhere in nature. You see them under a microscope. And what we're trying to do is really play those up to a bit more of a macro level than what under the microscope. And how can we start to create these new generation of materials that really involve design, not just at the micro level. Yeah.
Awesome. I think this gave us a really good overview, not only of the potential of lattices and additive, but also innately of the complexity of lattice structures. And I just remembered this as you were speaking, Nick. Dave, a while back, wrote a blog article called Put Some Lattice on It, kind of teasing the industry a little bit, where we saw a while back everybody just adding lattice structures for sometimes valid reasons and sometimes not valid reasons. It was almost a little bit of a trend to showcase visibly the potential of additive, but sometimes not really with a high value on it. And Dave, now you've been in the additive industry for a while, not only at OEMs, but also at users of additive manufacturing technologies. And you've now been through various programs where we've seen, prior to the approach we're trying to take now with a digital foam network, the conventional way of developing lattice structure applications. Can you take us through the typical or previous value chain and process steps that somebody had to take in order to get to an application that hits the performance markers they're trying to achieve?
Yeah, sure. Let me say thank you as well, Fabian, for having me on today as well to the rest of the group. I think as Nick already touched upon, you're just starting to see, if you don't already have experienced the complexity. So Nick just touched on one point on the star, if you will. So as the rest of the group talks today, I think it starts to highlight some of the intention and purpose around lowering that barrier. Points you mentioned, yeah, that blog article title was if you were a Portlandia fan years ago, with putting a bird on it. My prior roles, and just looking back, it felt like that's what everybody wanted to do. Instead of putting a bird on it, they just wanted to put a lattice on it. Which in the early introduction of that concept in additive, some of the early movers, you definitely get the visual demonstration, you get the awe, you also get the performance opportunities. I think anybody who then tried to go down that path, Mike also has a unique background and history with that as well. Like the reality of making that cross the finish line is certainly not to be understated. As you mentioned previously, I worked for a military helmet outfitter. Gentex is the name, in Scranton, Pennsylvania. And when I was brought on there right after my PhD work, one of the things they asked me to do, which is I think common for a lot of R&D leaders in their organizations, was go innovate on our product line, right? Whether it's traditional foam or just some sort of performance feature. And immediately additive is one of the pathways that you pursue. So I have a real experience being on the other side of this conversation and being overwhelmed also by all of the acronyms. I know when I first approached it, everything was an acronym: EOS, HP, SLM. It was, can't we use real words in this space, right? So appreciate the Arkemas and the DyeMansions of the world using a full name. But I went down that path, and each pathway in some ways is its own challenging endeavor. There are times where you feel like you're making progress, just working through the design or software aspect. And then you get to the next step and you realize there's different file conversions, technologies handle different strategies differently, powder-based, resin-based, then the demands of the post-processing on each of those technologies. And it starts to get quite overwhelming to really down select, when really our job as the engineer or as the product developer in that organization is you just need your product to make a leap forward. You don't want to, you don't need to, you often don't have the bandwidth to become an expert in computational design, an expert in thermoplastic or thermoset chemistry, an expert in vapor polishing, color. I've become a color scientist now from working with Mike, the different shades of purple and brown. It's incredible. And you can see how eventually, and a lot of organizations don't have a team of 10, 20 engineers working on this on the daily. Those organizations are unique. And I think there's a reason why they're the industry leaders. But a lot of times it comes down to one or two passionate individuals who are driving these things forward. And so now that I'm on this side, if you want to use that kind of metaphor, is I can empathize and understand. And really it's our job to help answer the questions they're asking and even help them become aware of the questions they're not even aware yet they need to have answers to. And really the phrase I come back to is just lower that barrier. And then if you think about the whole value chain, just like you said, each step can bring a lot of value its own way, and even just be optimized in a way that it can maybe be less of the pain point in the process, starting from the available kind of materials to then how those materials influence what kind of maybe simulation aspect or like lattice selection, how those lattice parameters can influence printability, and then all the way down. And Mike is living this is often, unfortunately, the post-processing step is sometimes one of the last things considered, when really that can be one of the most influential first impact components of the experience. And then if we have to make a tweak to something, we have to start all back over. So if the material isn't smoothing the way that, or providing a finish that they want, or the lattice design in the way that it's being finalized. So I think one of the intentions of the digital foam network is we're becoming more aware of how up and down the whole value chain, there's questions that need to be understood up front. And then really it's our job to act, I think, of like a spider web network to help constantly asking questions back and forth. Because each application or each customer is often its own unique snowflake, if you want to call it that, which is wonderful because they have their own specific space that they're exploring. But we often don't have all of the questions already answered. So it's this team here that needs to work together, huddle up and say, okay, this is what we're seeing in this upfront part. Or if it's a brand new material, how's it going to influence everybody's technical insight all the way down that chain? And some ways it's extremely fun. I think as an engineer, this is why you get to wake up in the morning and it doesn't get boring. But then at the end of the day, that same engineer it can be frustrating or challenging to feel like, am I making progress? Am I just creating more challenges? Am I just creating more questions? And again, I think that's where this network is designed to focus all of that, demonstrate we've done this before, and help become advisors up and down the process for anybody. And it's going to continue to evolve as the industry continues. Where it is today is amazing from where it was 5 or 10 years ago. And it's almost mind-boggling to think where it's going to be in 5 or 10 years from now, the rate at which technology is really evolving.
Yeah, no, thank you for that overview. I think it's very important to understand where we were before in order to have this conversation on about this network and collaborative approach, where that can take us. And really what you're trying, or what you are saying, if I wanted to summarize it, is we're shifting away from selecting a type of lattice, any of the lattices that Nick, you mentioned in the beginning. And then from there on, working our way towards the application, towards the material, towards the post-processing, but taking an inverse design approach where we focus entirely on the final properties that we're trying to achieve and then move our way forward from there. Now, from an application developer approach, and now this question is more of an open question to whoever wants to take it, and we can even touch a few points here before we dive deeper into each section of all of your expertises. How does this change the way now that we think about developing applications in the space of lattices compared to the past?
I can take a quick stab at it. I think like really what we're trying to do as a group here with the people, all the different entities that are on today's podcast, is we're trying to simplify things for the end user, right? I think a lot of times, as Dave already touched on, the end user doesn't necessarily care so much about is this a TPMS lattice? Is this a beam-based lattice? What's the node size? What's the strut size, right? What they care is, does it accomplish the end goal that I need it to achieve? And does it do it better than my existing solution today? And so I think by trying to work collaboratively, inverse that design challenge, allow the end user to really say, these are the criteria that I'm looking for from a performance standpoint, and then have a solution that's ready to go, or a very streamlined approach on how that's going to be developed, I think is really what we're trying to do to drive adoption as a collaborative group here, and just make that easier and more digestible for the company to say, hey, this is a no-brainer. Let's jump right in and start to adopt AM and these next generation that we're looking at.
Yeah, huge reduction in hurdles. I remember, Dave, when we had an intern, Paula Claris, who's now at Cumberland Additive, she looked into various lattice structures and different shapes and forms, and printed all these pucks and tested all these pucks, and trying to figure out which puck really meets the performance criteria that I'm trying to hit. That's a lot of effort to go into an application development. So is that really something that that all of us really can alleviate and simplify moving forward?
Yeah, where I'd like to see us get to, really, and from, if you come at it from a customer's perspective, is, like you said, thinking on the back end. They come with some performance set of requirements from a durability perspective, from a performance perspective, from an appearance perspective, and can we already identify what a solution space is? What I like to use the funny metaphor, and I realize this is now being on this end, is I think where we're trying to get to is, at the moment, we're a restaurant that when you walk in, we have a long list of ingredients for you, but we don't really tell you what those ingredients can make. So instead of saying we have this sandwich and that sandwich, which is how we're used to walking into a restaurant, we're saying we've got bread, we've got meat, we've got cheese, we've got sauce, we've got lettuce, right? Which is basically, we've got materials, we've got lattices, we've got printing parameters, right? We've got finishing techniques, which is like helpful. And maybe you're an expert. And again, we can go down that whole restaurant kind of metaphor later, but that's how I feel too, is really what this group here is in charge of, is how can we actually create finished kind of recipes or targeted solutions for application spaces. And I feel like we've uncovered, based on certain projects or applications that have gotten across the finish line, we understand some of those spaces, but I feel like it's very linear. I don't know that we have really developed comprehensive 3D solution space around that. I think that's where we all would like to get to. So when I think of the inverse way, I think of how can we create really this menu type experience, and then everybody else figures out on the back end how you're going to make it, as opposed to everything is a build your own pizza. Everything is a build your own, whatever it is, which can be overwhelming.
Yeah, if this is the first time you meet Dave, there would not be a conversation with Dave without a metaphor in that space, which I'm a big fan of. So let's stay with that, actually. So part of that sandwich is obviously the meat or the tofu, whatever you prefer, but it's also how you prepare it, right? What are the post-processing steps of the griddle? And I want to hear a bit more from Pierre and from Mike, because those are such key ingredients to a digital foam application, which is the material, which is the post-processing, to really achieve a visual and a performance of the part surface itself. Starting with you, Pierre, materials in additive manufacturing evolved from conventional materials. We just took what we had in conventional manufacturing and initially tried to copy that into additive. What does the material landscape look like today? How have we transitioned conventional materials into additive manufacturing? And what are some of the unique properties digital foam applications require that may need us to change and tweak some of the polymer recipes that we have today?
That's a large question, definitely. But
it's a loaded question, yeah.
But first, thank you very much, Fabian, for having me on this great panel today. Maybe on the last comment, you mentioned the inverse design, where we can play at I would say at the material level. This is also very important in this collaborative space, as Nick mentioned. We have a role which is also to enable that everybody has the right data in the models, to ensure that the results from the design and from the simulations, they match the reality, basically. So in the end, everybody want to simplify the first relevant data whenever you put the right data in a model, you get better results. So at the very beginning in material and polymer science, it is key to have this very strong background. And back to your question, which is large, basically, yeah, maybe I can answer with the Arkema journey on polymers and in additive manufacturing. I would say that first, at the global level, Arkema, we are glad to manufacture polymers that are versatile in the sense that they can be processed in many processing technologies like extrusion, injection molding, rotomolding. If we try to have a focus and go more into details, if we focus on the polymer, which is well known in AM, which is our flagship polymer for 3D, which is polyamide 11, for instance, there is a great legacy.
Mhm.
As you mentioned, polymers, they have been here in the world for a long time, but for 3D, they are more recent. Polyamide 11 was invented more than 70 years ago, 1947. So it's nothing new, but for AM, it's quite young. And it has been a reference for in the world of engineering plastics for a long time because of high performance. I won't go into this kind of detail. It's also well known because it's a bio-based polymer, but it's not that simple to go from the pellets that we sell for injection molding to a powder, which is basically the major use in powder bed fusion technologies in SLS or MJF. Sorry to use acronyms on that. But the first question for us is how do you manufacture basically powder? And the key question when we start development like that is what kind of powder do you want to manufacture? How do you characterize it? Is it with a morphology? Is it with a granulometry properties of the powder itself? But we have to relate them to correlate with the part properties in the end, because what we want is that we need to ensure that the applicative properties are good. Does it process well? Does it allow the end user to produce performance parts? And this is the trick, characterize part properties and to find the right way to correlate it to the powder properties. And this is a multi-level concern. It's not only one characteristic that goes to the other. Usually it's more difficult than that. So I would say that unfortunately it's not straightforward to start from a polymer that you know and to do it, to make it available for AM technologies. But once again, collaboration is key, because what I can highlight is that we don't develop materials at Arkema without any collaboration, without any understanding of the technology that will be used to process the material. And this collaboration is the key to have a success between the printer manufacturer, the material manufacturer. In the end, more globally can be produced with the specific designs and also with the post are technically demanding.
Yeah, no, thank you for elaborating that. I think it's really important to understand for people that a PA11 that's injection molded is not the same PA11, probably chemically and from a final performance that you'll see at the end part of an additive application.
Chemically speaking, this is still PA11. So this is always the polyamide 11 and the same bio-based structure and so on. But definitely between a pellet and the powder, things are very different. And the way to process and to start from the monomer to get the polymer in different ways, definitely.
Okay, yeah, agree. But let me ask you one question though. So if we talked about PA11 a lot now, in the space of digital foam, what other materials gaining interest today that are opening up a new space of applications in additive? I'm also very interested in more rigid applications. But could you give us an overview of some of the more interesting developments that you guys have been working on, but also some of the increasing demands that we see in the market?
Yeah, you mentioned rigid materials. Let me start also with rig materials, because this is where we see also trends and interest from users. Basically, elastomers are valuable when using lattice structures, because everywhere where you can create dampening effect for comfort zones, seats, automotive, for bicycles, or protective things like helmets, definitely elastomeric materials, they play a role. It's also a way, sometimes fashion is also elastomers for design. They could use also AM for rapid prototyping with soft materials. It's not only always about rigid, but in terms of rigid material, definitely we see traction because of the people wanting to change the designs. And once again, your initial question about inverse design is critical, because everywhere where there is lightweight, there is possibility of improving the way we create the parts. It means also smarter designs for energy absorption. I think, Nick, you mentioned that earlier in the beginning. It means also optimizing system efficiency, which could be key for turbines, for instance, in the energy domain. And for us, as the material supplier, I think there are different ways to try to grow the cake, because in the end, it's always about finding new application and grow the cake of additive manufacturing. The first one is by decreasing the cost per part, because economically speaking, a new application to grow, and big cost of the parts now is still in the cost per part via the recycling and the refresh rate that you have for powders. So enabling higher recyclability in materials is a key trend, and that will definitely benefit to digital form applications. And the second one is to grow the cake by enabling more applications and address new markets, which means also development of new materials with specific properties to fit. In that space, it goes from high strength plastics to specific conductive grades, fire retardant solutions. And in AM, definitely, one more comment is that we are still very limited in terms of materials compared to what you have in injection molding. For P11 in pellets, you may have 100 different grades and really different compounds with specific additives or specific formulations that can be used by injection molding. And for additive manufacturing, if you have 10 grades, it's already very important. So knowing that the industry is still very young compared to the other is great for us, because it means that we have to innovate. We can innovate a lot and find new ways of addressing new markets. But yeah, there is a lot of space for materials to be developed there. Maybe one more comment, I think. It's about sustainability. And once again, it's like sustainability globally, because of when you redesign things, you can also use less material. But in 3D, in a sense, which is always compared to a subtractive manufacturing method, it's supposed to decrease the amount of waste, and materials with low carbon footprint, bio-based background, and so on. Definitely, they are
100%. I think you touched on a lot of key drivers for digital foam applications, and I think all of us are on here today in order to increase awareness of the potential, increase awareness also of some of the challenges that still exist today, because I think inflated expectations are one of the worst things you can have when moving into such a project. So I think it's important to mention these as well. One thing we haven't touched on yet that I think is super crucial is obviously post-processing. And what's interesting is just because post-processing comes last in the process step doesn't mean it comes last in consideration for your final application. And I think that's something that you, Mike, and the DyeMansion team sometimes struggle with as well, is that it's such a crucial step to a final application. All the applications we've now seen in the past year, we've had Nadine from Wilson on here with arguably probably one of the most famous applications in the industry, the Wilson prototype basketball. We've had Bauer on here with also a visual digital foam. All of these applications wouldn't be the applications they are without the right post-processing technologies. Mike, can you take us a bit through the importance of post-processing in digital foam, and what are some of those key technologies that people need to be aware of and need to consider when developing an application?
Yeah, absolutely. First off, thank you for having us on here, Fabian. It's always exciting for me to be on a panel, something like this, where I take a lot of joy sitting back and listening, because coming into this over a decade ago, it is super easy to create lattice in anything you want, but it becomes an entirely different story when you want to be purposeful with that lattice. Nick and I have talked about this many years ago, and some of my background was on consumer product, footwear, protective gears. And it goes down to that very first question is, what do we want this to do? You just mentioned two really exciting projects, right? We have a helmet and we have a basketball or an airless prototype. Two entirely different needs. One needs a dampening effect and one needs rebound effect in a different way, right? So to immediately start thinking, it's not just about the material that's coming from someone like Arkema. It is, how are we going to use that lattice structure to actually influence what we're trying to get out of that part? As it's already been alluded to a few times, the post-processing step is usually thought about last. And it's not by any fault, it's just because it's the last in the process chain. And it's generally been handwork for most of the existence of additive or traditional manufacturing. It's been a lot of handwork or skill sets that has become more automated over the last years. Ourselves, of course, as our company have been able to create ways to automate some of this. And it's also created ways where now we've exposed some of the challenges that we see early on. One of the first things that I've seen
in my experience on when I first started getting into like the elastomerics on consumer products, especially in footwear, was what happens when we put a beam directly into a really thin skin. And forget the idea of the thermal issues you might see on the printing side. It's now we go to color it and we hand it off to a designer or the next stakeholder. And we have two different colors because, well, we didn't know why at the point. Over many, many years, we started to understand what's actually happening here. And it all has to do with how are we positioning it? How are we actually influencing that lattice into an adjacent location, whether it be a thin skin or maybe it's a really tight lattice that morphs into a looser lattice cell structure or a larger cell size, for example. Then we have to play, how are we going to print it? What orientation do we print it? How close to another object can we print it? And then one of the most fun things that Dave and I spend a lot of time on is how many can we put into a build and have a successful part? Forget cost here because that's just going to hurt us when we really realize it at the end. How many can we really put into a build and still maintain that throughout the entire build? Whether it be on a P3 system or P7 system, now we have another influencing factor. And we haven't even gotten to post-processing yet. Post-processing is really where we just expose a lot of this because there's color adhesion, which is one of our steps, and then there's smoothing, both of which are thermal processes. So we're introducing that polymer into another thermal exposure. Then there's a chemical binding that takes place in the coloring. If we have different density properties, then the color is going to adhere slightly different. Or if we have a really thin structure versus a thick structure, the light's going to transfer slightly different through that part. So visually we'll interpret color different. And these are all things that we identify at the end and it becomes too late. And this is where I really enjoy sitting here because a lot of the times when I first get onto a phone call with a customer or potential application, it's very much understanding where in the prototype phase are they and how can we start that, not to say over again, but how can we push it back so we start to realize what we do with Nick's team will influence what happens from Dave's team and then changes how we have to protect it from us. And at the end of the day, of course, the stakeholder or the designer, whoever is that last person on the inside, they have to understand that and they have to work through it. And kind of Dave's analogy coming from the restaurant days quite a bit. I love it because it really is just a bunch of ingredients, right? And everyone wants to order that perfect meal, but you might have to use 10 different ingredients depending on where you are or how you want to approach it. So yeah, the post-processing step, there's a lot of different influencing factors to it. The most important things is understanding how do we create a more natural or organic transfer of the energy that we see throughout the entire process. I remember having a conversation many years ago with a material chemical expert, and I'm by no means one of those. And when I first started to say, hey, why can't I smooth this part? And it's the same exact part, I think, to this one. And the first question is, he said, how many different processes are you going through? And we thought about it. Okay, we make the material at this temperature, then it transfers or ships somewhere. Then it gets printed at this temperature, cools down to another temperature. It gets depowdered at a different temperature with another influence of material on it. Then it is handheld, sometimes hopefully with gloves or in a good area. Then it goes into maybe a smoothing process where it's elevating and decreasing temperatures. Then it sits and then goes into a color process where it goes back through another temperature. And as I'm explaining this, I'm watching the almost disappointment coming from this material chemist's view of, my gosh, what have you done to that polymer? Over this many exposures, ups and downs. And it just became this roller coaster of, we really need to start thinking at the end to influence the beginning. So it's been exciting to be on my side of it because I played on all ends of this and I get to have the last push on it sometimes.
Yeah, in the past you were right at the beginning and now you're at the exact opposite end. What I do think helps people to develop design applications is to truly also understand the processes that are involved. I think most engineers now know how a laser powder bed fusion process works. They understand oftentimes the different types of lattice structures. I don't believe they really understand the post-processing technologies. Or don't spend really time. Could you spend a couple of minutes explaining to us, especially those two core technologies of dyeing and smoothing, what really happens in the system and what happens to the polymer?
Yeah, absolutely. I'll actually start one step before that a
a lot of people forget about is depowdering step, but it's actually one of the more influential parts because most shops around the country or even around the world, you're using manual labor, and it's very effective, of course, in many ways. You have a lot of skilled folks that can do it, but the challenge becomes we stop thinking about, are we just depowdering it or are we potentially changing the surface slightly? And one of these big things is, are we using glass media to depowder? Are we using ceramic? Are we using dry ice? What are different methods of depowdering that all have a different factor of how we influence the surface? Glass, probably the most commonly used across the globe here. Extremely effective because it can break down, creates smaller particles, cleans better. But the one thing that we forget about is that it also creates fragments that could potentially embed themselves into the part. Usually, that doesn't mean anything for most projects or basic R&D stuff. But if we color that or smooth it, the glass doesn't smooth and the glass doesn't take color. So now we have a new influencing factor that generally is overlooked a lot of the times. So one of our core technologies is around depowdering, and it's really a simplified version of how do we minimize human risk or human error into depowdering. Fixed nozzles, a rotating drum to at least manipulate parts so we can get cleaning in all areas. But it's really about the distance and duration of blasting of media onto parts. And it's really just creating uniformity. That's all it's about. And then moving it into the next two main technologies, as you mentioned, we'll start there. Color is an amazing world, right? You've got your bread and butter of your red, green, blues that you can pretty much get down at any grocery store across the country here. But if you want to have a repeatable color, you have to really start thinking about, what is the recipe in this color? Then we talk about, as we said before, something like the Bauer helmet or the Wilson basketball. What is the application doing? It's being bounced on a wood floor hundreds of thousands of times, full life, right? But we're talking hundreds of times. A helmet has impact, has sweat. All these things could impact how that color is maintained on the part. So traditional spray painting methods or basic dip dyeing methods, they may not last. That color may come off of it because it's really just staining the part, or it's an added shell on top. So the way that we do color is through an actual color adhesion. So it's a color binding to the polymer links themselves. It goes all the way back to Pierre's world of what is the polymer that we're working with? How many linkages do we have? How is it affected in the print? That gives us more ability of, can we bind that color pigment onto that part? Generally speaking, we'll go anywhere from about 175 to 250 microns into the part where color is adhered onto the polymers. This is really important because it allows us to get through some of these 10,000, 100,000 cycle tests that a lot of the industries use. It also gives us the ability to get into markets like the automotive world where UV exposure is a really big risk. And it minimizes some of the effect of color bleed over time or color wear over time. The importance of repeatable colors is key when we talk to some of these bigger customers because a lot of them have their own seasonal color palettes. And a lot of the times they have color experts that speak in a different language. But almost every single one of them utilize a color chip of some sort that is not 3D printed. It is almost always a standardized color Pantone chip or a code of some sort of hex code or RAL code that doesn't truly translate just to any 3D printed part. To Pierre's world of the PA11s, whether it's a PA12, whether it has the whiteners in it or not, that standard Pantone chip is great, but we have to take an entirely different course of action based on what the material is. Then Nick and Dave can jump in and start talking about the influencing factors of how that lattice could affect it. Dave can talk about the print and the build capacity. All these things are huge factors because sometimes the truth of it is we might have a standard PA12 off of an SLS printer that is maybe an EOS based printer. And then we have another comparable SLS printer. That same PA12 will likely have some variance in color, even though the exact same color is used, just because we have different effects from laser powers, energy that's being put into the part. So it goes down to true recipes and how we actually have to work with those. We've come up with ways to minimize some of that risk over time by creating cartridges that are based on scanning, using RFID tags to scan a cartridge. So it minimizes that human interaction of how we're creating the recipe of color. It's pretty darn good. We can create repeatable results across the globe on various machines and at various altitudes or humidity control areas too. So as long as we're within range or a spec, generally speaking, we can meet just about the colors that are requested in a repeatable way across different platforms. Now, we'll definitely see some areas of challenge. One of my favorite backstories is with the footwear side of, we started coming around. We were working with an early elastomeric material with EOS printers and some other SLS printers. I remember very distinctively, we had 5 or 6 very good colors that we liked, and they were all on the darker range. And we went to the designers, we walked through it. We said, all right, these are the ones we can work with. You can do just about everything within these ranges as long as you don't go lighter or grays. Designer chose gray right off the bat. And then we went through this several month process that we joked around and called it was the 50 shades of gray of 3D printing, because we could never truly hone in on it. And it was a footwear product, so we were always comparing a left and a right. And so it became a challenge for sure. And it was always a joking thing. And this is many years ago, we still hint on it. Yeah, so color is definitely an interesting topic. We've created ways to help, as I said, mitigate that risk deviation between parts, types of materials. As we get into smoothing, the general concept of smoothing is quite simple. We're basically using a solvent. In our case, we're using a benzyl alcohol that is basically vaporized and released into a chamber where the parts are suspended. That vapor then creates condensation on the parts, allowing those molecules to microdissolve and reallocate themselves in a tighter form. And then that vapor is removed. Based on the material and what we're trying to do, we influence it many different ways. We can either change the temperatures, we could change the introduction of solvent, we can change the duration, the times, many different levers that we can pull. But it's all about creating exposure of solvent and temperature onto a part. At the end of the day, what we're trying to do is create a sealed part that visually looks glossy and very smooth, but really we're just creating tighter bonds of the molecules where it's now a washable or more usable surface. The inherent side effects of this is that it becomes washable. So now we can talk about things like medical applications because we can clean easier. Becomes a more appealing part in the consumer world, right? Now we have things like our helmet where we have contact to skin. It's more comfortable sometimes compared to a rough or fuzzy part, for example. And then areas like the Wilson basketball, we actually had to influence that smoothing effect quite a bit to more mimic a hand feel of an already existing product. So we have to really play with some of these levers, and all based on what the material is and the influencing factor of how the lattice comes together to create that generic shape or the organic shape. And then how do we print it? Are we putting 3 or 4 of them in a build or 100 in a few? It really plays a factor on how much thermal energy is put into that part. That in turn translates into how much energy we can really affect it. So it's an interesting process chain, but yeah, in a nutshell, that's how they work.
No, thank you for that, Mike. I think it's so important to talk about these technologies and give people a better understanding on how they work. Nevertheless, we always have to start with a digital file, a CAD file. So back to you, Nick. Now that we talked about materials, we talked about post-processing. Dave talked about even within the, in this case, polymer laser butterbed fusion process, we also need to find our recipe and develop our process parameters for certain materials. And maybe we can touch on that in a second, Dave. But how do you take all that into account in the design phase? And how are you helping developers to hone in on all of these aspects from the...
Yeah, it's a really good question. So we think of it almost as like in the more traditional manufacturing sense of tooling, like what we commonly internally call digital tooling, right? How do we develop a standard operating procedure that takes into account the entire digital thread of everything that's going on? What are the parameters of the lattice that's being used? First of all, what is the base material that we're using? What are those properties? What are the design parameters? What are the print parameters? And what are the post-processing parameters? And it creates that formula. That's to go back to Dave's analogy again, that's the sandwich, right? We're taking all these ingredients, we're tuning them, we're getting them just the way they need to be, and then we're trying to them in, right? And say, this is how it's done. And now we have a repeatable recipe that we can go back and start to use. And I think that's a really important part with 3D printing, is because it's like a double-edged sword, right? We have all of a sudden, we have all this design freedom. We have no molds, no tooling. We can make whatever we want. Awesome, right? But at the same time, the repeatability factor then really shoots up in terms of challenge. And so having that digital thread, having that digital tooling and tracking all those parameters is really important. So at General Lattice, we're really focused on developing these sort of meta materials, right, that are meant to replace existing materials in the market today. They utilize lattices and the advantages that they bring from a performance standpoint. And so when we go and develop those, we work directly with the OEMs. So we're working directly with the material manufacturer, we're working with the hardware manufacturer and the post-processing to build out that digital thread so that when we present data and information about that metamaterial to the customer, we already have that kind of consolidated and defined in a way that we can start to ensure repeatability. And it's also, when you look at production too, you have to think about the supply chain side of things. You have to think about who is the vendor that's actually scaling this up and working with those people. So it's truly end to end, needs to be coordinated and organized in order to get that customer that repeatability, ensure the quality, and do it at a scale that is actually upsized.
That's super helpful. And it's important to bring all of these steps together in the beginning and having a tool that people to look at it from an inverse design perspective. Dave, you've worked with various clients now developing applications in that space. How do you start? If I come to you now, we're all wearing headphones. Let's say we all have a soft, somewhat comfortable foam piece here. I want to print that now. I want to launch an additive snack headphone line. How do I approach it? And how do I then engage also with Nick, with Arkema, with Mike? What's the best way to approach it?
Yeah, really good question. I think Mike touched on this already, is the intention or the purpose. And sometimes that intention or purpose can evolve, or they think they know that's what they want. We want a 3D printed headphone foam for a very radical experience, right? Or a new type of product. But really, then you think about it from a technical perspective. What is it you're wanting that to actually do? And how the factors that a digital foam solution can bring influence those. So if it's sound reduction, can you now understand how a lattice structure can influence different kind of acoustic properties? The skin contact, Mike talked about that. Okay, now you're going to have direct skin contact. I'm not a tissue expert, but the way that your ear receives contact compared to, let's say, your chin wearing a helmet, right, it's going to be very different. The approach can be, I think, a good conversation of listening and question asking. And then I think also sometimes you have to be a little bit rigid on our side about what's possible. It's easy to say yes, have that first meeting end, and then go back internally and say, I know we said yes, but can we do this? Which I think was maybe some of the earlier years ago type of, you don't want to lose that opportunity, right? And so I think we're getting a little more mature, and sometimes the answer is no, or the answer is we would need to design and develop these types of solutions, which can be a challenging conversation depending on how much is needed from a personnel, resources, funding perspective. I think that's another thing that this group is working towards, is making that leap into it, or making that journey into it easier and more financially reachable. Inherently, all the work they're doing is cutting edge and innovative, but it can't be cost prohibitive in that sense. So that's where, again, can we create solutions? Can we become more automated? So those, like I said, everybody's question is often an individual pursuit of an application. So you have to be really good listeners, and also in some ways see what it is you have available, and just have some good, honest conversations, I think is helpful. And I think it's also, you'll see growth in a little more of the ability to share publicly information. I think there's more dissertations being done at an academic level, more data sharing. The more that we can make this information available, more people can think about it, digest it, and add to it. So I think that's also a big step. But as this panel demonstrates, There's two perspectives of all these engineering variables. One is it's anything can be tuned, and so anything's achievable, or you may be listening to this going, it's incredibly overwhelming. There's so many variables, so many steps. And so I think both of those are true. And this is just how we will get better at what we do. And through incredible applications and opportunities such as the basketball, huge leaps are made in this space. I think everybody benefits as a result.
Yeah, and I think we had Theory from Bauer Hockey on this podcast as well, and I think he shared a similar story, which was, you just need to have a lot of conversations with all these different players, but most importantly, really understand the technologies. And I think today, my hope is that we were able to shed a bit more light into each subsection of the process chain. We talk a lot about the printing process, and I don't think we need to repeat it within this episode, but obviously, there's a lot of process parameters that also within the printing process we can manipulate and have to manipulate, especially for lattice structures when it comes to how we run the laser, what layer thickness we run, what orientation we print the part in order to get all these repeatable end-use results that also you mentioned, Mike. Before we jump off, I am very curious to hear from you guys. Which industries should listen to this episode? We know that consumer guys are already pretty deeply looking into digital film technologies, but what other industries should be listening to this and should seriously consider adopting digital film for some of their applications? Do you guys have any thoughts?
Yeah, I think the medical device industry is like a huge opportunity. I think when you look at, again, a comment I made earlier about ingredients for success, right? How can we make a truly better product? And when you think about med device, you think about personalization, right? Which really takes advantage of the design freedom that AM provides, as well as the digital foam development. And how can we make better metamaterials that are more bone-like and growth better? How can we make the patient feel better at the end of the day? And I think that's a huge opportunity. Obviously, there's more barriers to entry with FDA approval, regulations, stuff like that. But what is one of the biggest users of AM technology today? It's the dental industry, right? And it's because it's personal. You can easily personalize. It's got the right build size for a lot of components. So I think med devices is a huge opportunity for growth within the AM industry for sure.
Especially for polymer digital film applications. So we don't see too many in medical today, I would say. But certainly interesting, especially because we have skin contact approved medical devices in polymers. So yeah, very good point. What else? Anybody have some other interesting industries?
Maybe just in medical, one comment. There are maybe not that much applications for digital form. Finding lightweight solutions. If you're talking about helmets, like cranial remolding helmets for babies, definitely you need it to be comfortable with the sweat, with the aeration and everything. So changing the design, maybe not to lattice structures, but to something similar, which exhibits the same performances and the same comfort. This has value. And going to this on lightweight, once again, I think aerospace and defense is definitely, they are setting trends in lightweighting because they need to do lighter designs, smarter designs, both to optimize the efficiency of the systems, but also just because of the decarbonization roadmap we are all in, and lightweight is part of it. So they are really setting trends in this domain.
Yeah. You mentioned helmets, right? We have hockey helmets, but we have soldiers that still run around in very hot environments with conventional helmets. Certainly a very interesting application that, as far as I know, has not been pursued yet.
Yeah, I was actually just going to comment on that. To the first question of what is the application intended to do? Do we think our helmet? One of the first reasons was it was about creating airflow, drop the temperature of the athlete. As you just mentioned, with soldiers out there in the field, cranial helmets for infants, for example, helping create their passageways for air. Taking those same thoughts and we start moving into industries like the aerospace industry, like the agriculture industry, we have to really think about what else does lattice do besides just create damping and rebound? That's the consumer market, right? Those are no-brainers, but we start looking at, are we creating passages to drop temperature? Really changes the idea quite a bit. So for me, those medical for sure and aerospace, definitely the two largest verticals. We can broaden the horizon quite a bit. an automated process in lattices.
Yeah, I'll add just a little bit there. So I actually walked around the Foam Expo, which is the show focused around foam. It's every year. And it was interesting because I think really that's where you need to go and learn about different ways foam are being applied. And I think everyone's touched on a few more spaces, but I've had people contact me about applications. So that's the way foam is being used. And when you go there to the Foam Expo, you certainly see a lot of what we've already talked about, but on the fringes is where you see some interesting uses for it. And I think that's where it's helpful to know that we've at least got the attention of those spaces, but there's still some leaps to be had regarding either can you print that fine or can you provide sound damping, other aspects. And that's where I think it may not just be SLS solutions that can provide that, right? There's other types of technologies that can print finer, but still if you think about just taking a material, assigning a lattice in a digital space and printing, that's quite interesting to think. I've seen some images of things balancing on fingers and those types of really like micro lattices. So I think that's an interesting space. But then as the SLS technology grows, the fine detail resolution, so as powder particles get smaller and laser focus diameters get more precise, it does start to open up those application spaces as well. Yeah, I'm hopeful to see it go into other spaces because I think in some ways there's a broader use or a more higher volume use, and that just drives more innovation for all of us.
Sure. I think the most important factor is to also make this less daunting for people to look into, because it can certainly feel daunting to engage in a development project if you don't have any additive experience and you consider all these steps that we talked about. And all of you really help the industry to reduce those barriers on a daily basis. Thank you all for sharing your expertise with us today. Thank you all for also giving us some insights into your technologies, into your developments. I think it definitely helps people to understand the process chain and the value chain way better, and also understand it's not potentially that challenging as I may have thought. So thank you all for being on Additive Snack today.
Thank you, Fabian. Thank you,
you.
Dave, for the
Thanks,
mental
Fabian.
picture of the
croissant for you. Yeah, it's a sandwich over here. A croissant in French. But yeah, to our listeners, I really do hope that this episode gave you a better understanding of the full process chain, of the complexities and of the opportunities of digital foam. I think it really highlighted that the additive manufacturing industry is not just about the printing process, it's about all the players, all the pre and the post processing that needs to happen. And it's about the visionaries, like the folks here on the show today, that really help us drive the industry forward and bring visions and innovative ideas to light. So thank you all for tuning in. Make sure to subscribe to Additive Snack to not miss next week's episode. And I'm Fabian Alefeld, your host, and I'll see you next time.